This is a video about estimating humanity's first mathematical constant, pi. In our modern age of computing, we've been able to calculate pi to millions, billions, and even trillions of digits. But for mathematicians of the past, like Liu Hui, these values of pi remain obscure from view. The year is 263 CE. Dissatisfied with the results of his predecessors, Liu Hui set out on his own attempt to estimate the values of pi. Unlike the ancient Greeks, who used the perimeter of inscribed polygons to estimate pi, Liu Hui used area, but he needed a formula to help him do that. Take a circle and draw a hexagon inside it. A regular hexagon can be divided into 6 equilateral triangles. Comparing the hexagon to the full circle, you might notice that there's still plenty of space between the edges of the hexagon and the curve of the circle. As you may know, a hexagon is a 6-sided polygon, so we'll refer to the number of sides on a polygon as n. And so as we double the number of sides on a polygon, turning the hexagon into a 12-sided polygon, 24-gon, 48-gon, or 96-gon, you might notice that our original polygon starts to look like a circle, and you're not wrong. As we approach infinity, the polygon's shape becomes indistinguishable from a circle. This isn't entirely unlike how your digital display works. While tiny pixels aren't round by nature, hundreds of them can form a circle. Now, if you took the excess area between our original hexagon and our 12-sided polygon, you'll notice you can actually form 6 triangular wedges. Curiously enough, rearranging these triangular wedges with our 6 equilateral triangles eventually forms a rectangle. While the height is simply r, or the radius of the circle, the length is half the perimeter of the polygon, or as the size of the polygon approaches infinity, half of the circumference of the circle. Discovering that the area of the circle is 1/2 times circumference times r, and since the circumference is 2 pi r, we can conclude that the area of the circle is 1/2 times 2 pi r times r, or pi r squared. So, with the formula for area of a circle in his hands, Liu Hui had the necessary knowledge to begin his attempt. Using the formula pi r squared, Liu Hui began with a circle with a radius of 1. This means its area is equal to pi. He first described a regular hexagon inside the circle, representing the area of this polygon with a of n, where n is the number of sides, in this case 6. Then he inscribed another polygon with double the number of sides, a 12-sided polygon, designating its area as a of 2n. Here we created our lower bound, describing a of 2n as less than the area of the circle, or pi. Nevertheless, it became apparent that the area of the 12-gon remained smaller than the area of the circle. So, Liu Hui overlapped these two polygons, visualizing the difference with the expression d of 2n equals a of 2n minus a of n. For our purpose, we'll visualize this as these small red triangular slices along the hexagon. Then, Liu Hui took each of those red slices, cut them in half, and rotated them outward. By doing so, he extended the area of the polygon slightly beyond the area of the circle. Liu Hui represented this mathematically as a of 2n plus d of 2n, which he set as the upper bound. Now with our lower bound and upper bound, we have essentially discovered that Liu Hui's pi inequality, a of 2n, is less than the area of the circle, or a of c, is less than a of 2n plus d of 2n. And since our circle's radius is 1, we can denote a of c, or the area of the circle, as pi. So a of 2n is less than pi is less than a of 2n plus d of 2n. In order to estimate pi, we'll return to our diagram. As is the case, we'll begin with an inscribed hexagon. Currently, we've determined Liu Hui's inequality and area of the polygon, which we'll determine as the apothem multiplied by the number of sides in a polygon times the side length of the polygon all over 2. Since we've established the radius of 1, the side length of our 6-sided polygon will also be 1. But we still need to find the apothem. So what exactly is an apothem? Apothem is a line drawn from the center of the polygon to the midpoint of one of its sides, which will form a right angle. Now here's the neat part. We can represent the apothem as just the height of one of those triangles that make up our polygon. By using the Pythagorean theorem, we'll be able to calculate its height with a radius of 1. The apothem, or height, is the square root of the radius squared minus half the side length squared. For the hexagon, that works out to be the square root of 3 over 2. By replacing apothem in our area formula with square root of 3 over 2, we can find the area for our hexagon. In the same way, we can apply this process to a dodecagon. Using Liu Hui's iterative method, we can calculate the side length of the polygon with twice as many sides. In this case, a 12gon, or a of 2n, equals 3. With a of 2n and a of n solved, d of 2n becomes 0.401. Thus, we've concluded that 3 is less than pi is less than 3.401 using a hexagon and a dodecagon. Liu Hui would eventually go on to utilize this method with a 96gon and a 192gon, accurately calculating pi to 3.1416. Certainly, this method has been employed by following mathematicians. For example, Chinese mathematician Zhu Changzi used Hui's method through a polygon with 12,228 sides. He determined that pi was between 3.1415926 and 3.1415927, a record which stood for 900 years. Through this method, we were able to determine pi accurately up to 9 decimal points using a 196608 gon and a 393216 gon. Here's a link to my Desmos page if you want to interact with this method yourself.